In this video, we're going to look at redox reactions. What sets redox reactions apart is that we're looking at the transfer of electrons, where in other reactions that we've looked at the movement of the atoms, where in redox, we're looking at the movement of the electrons. In redox reactions, one species is going to be oxidized and the other species is going to be reduced. Always, if you have one species being reduced, you have another species being oxidized. They're always going to occur in pairs. So we can use the mnemonic devices oil rig and Leo says grr to help us remember. Because in oil rig, oxidized is lose. So the species that is oxidized is going to lose electrons. The species that is reduced, so in our oil rig, reduced is gained, because the species that's reduced is going to gain electrons. And we can also remember that with Leo says grr, with Leo being lose electrons oxidized, gain electrons reduced for the grr. So there are two easy ways that we can remember the transfer of electrons in our oxidized species and our reduced species. So now the first thing that we have to do when using redox reactions or in working with redox reactions is to assign oxidation numbers. Oxidation numbers are going to help us predict how the electrons are going to be transferred and predict which of our species are going to be oxidized and which are going to be reduced. So let's consider the compound NO2. We know that the oxidation number for oxygen is always -2. We also know that for hydrogen it's always +1 and for fluorine it's always -1. So every time we see an oxygen, when it's bonded to another element, we know that its oxidation number is -2. Since there is no positive or negative charge on this compound, we know that the overall charge of NO2 is neutral. So our overall charge right now, with two oxygens each having a -2 charge, is a -4, meaning that in order to make this entire compound neutral, the oxidation number on our nitrogen must be a +4. If we look at the compound S2O3, once again we know that the oxidation number on oxygen is -2. So now with just my oxygens I have a total charge of -6. So the charge on each of my sulfurs must be a +3 because I have two sulfurs. So +3 times 2 gives me a +6, because once again the overall charge of this entire compound needs to be neutral. So the charges from my sulfur need to balance out the charges from my oxygen. But now let's say I have a compound that doesn't have an overall neutral charge. So if I have C2O4 and this molecule has or compound has an overall charge of -2. Well, I know once again that my oxidation number for each of my oxygens is -2. So with just my oxygens, -2 times 4, I have an overall charge of -8. If I wanted that to be balanced, each of my carbons would have to have a charge of +4. But I need this entire molecule to have an overall charge of -2. So essentially, I can set this up algebraically by saying -2, the overall charge of the molecule, equals X, my overall charge of my carbons, plus -8, the overall charge of all of my oxygens. So I need to figure out what the charge on X needs to be. So if I solve this equation, +8 plus 8, I get 6 equals X. So my overall charge for my carbons needs to be a positive 6. But since I have 2 carbons, that means each of my carbons has a negative 3 charge. So negative 3 times 2, positive 3. Positive 3 times 2 gives me a positive 6. Positive 6 minus 8 gives me negative 2, which is the overall charge of this compound. So that's how I can assign oxidation numbers to compounds that have a positive or negative charge and aren't just neutral. The only other thing to remember about oxidation states is that if you have an element by itself, like nitrogen, or bonded to itself, like O2 or I2, their oxidation numbers are going to be 0. So only when a compound or an element is bonded to a different element is it going to have an oxidation number. If it's all by itself, as in the case of our nitrogen, or bonded to another atom of the exact same element, then its oxidation state is also 0. So, to review our oxidation numbers. When assigning oxidation numbers, you have to first look at the overall charge of the compound. So this compound has a neutral overall charge. We know hydrogen is one that we always know the oxidation number of. It's a +1. Oxygen is another one that we know the oxidation number of. It's a -2. So -2 times 3 gives us a -6. And our hydrogen has a +1. So in order for this entire compound to be neutral, we know that nitrogen must have a positive 5 charge. We also know that with compounds that do carry an overall charge, that we need the oxidation numbers of the elements in that compound to add up to the overall charge of that molecule. So oxygen, again, we know has an oxidation state of -2. -2 times 3 is -6. So our carbon must have a positive 4 charge, because positive 4 minus 6 equals -2, which is the overall charge of our compound. And we also know that when we have elements on their own or bonded to an identical element, that their oxidation state is 0. And then the next video we'll look at how we can use the oxidation states to help us determine reducing agents, oxidizing agents, determine which species are being oxidized, which are being reduced, as well as total transfer of electrons in a reaction.